All right, welcome back. In section 4.2, we'll be looking at the fundamental theorem of calculus. Our goal in this section is to find an efficient way of computing the definite integrals by linking the definite integral to the indefinite integral of chapter 3. Remember that g of x plus c, so we'll need to find a link between the integral that calculates area and the integral that gave us just an antiderivative plus c. All right, so to achieve this, we will start by studying the properties of the integral. Then we'll be able to state the fundamental theorem of calculus, which give us an efficient way of computing the integral of f of x dx. So just to show you how efficient it is, I will recompute a problem that we did with Riemann sums. I'll compute it with the fundamental theorem, and you'll see it's going to be so much quicker. You'll like it. All right, so section 4.2.1, properties of definite integrals. So in proposition 4.2.1, I'm going to take a, b, and c and m to be real numbers, and I'm going to have two functions, f and g. All right, so first property, if I integrate from a to a, so the two bounds are the same, then I'm going to get 0. Now, if I integrate from b to a, so my bounds are flipped, if I want to relate it to the, let's say, normal one, which had the integral from a to b, then all I have to do is add a minus sign in front of it, and those two are the same now. If I'm integrating a constant, then I'm going to have m times b minus a. If I integrate a sum or a difference, I can split it as two integrals, and then you keep the same. If it's a sum, you keep a plus. If it's a difference, you keep a minus between them. All right, if I have a constant times a function, again, I can pull that constant out. And then this one is the most interesting one. You can actually split an integral. If you want to go from a to c, you could first go from a to b, and then go from b to c. So I like to think of it as making a pit stop at B. B might be anywhere. It might be before A, it might be between A and C, and it could be after C. It doesn't matter. This identity will be true for any value of B. All right, so these are not going to be proven. I'm going to give you a sketch of why some of them are true. Really, that sketch I find very helpful when you're doing problems, and that's why I'm giving them to you. All right, so let's look at the integral from a to a. That's going to be the net area of the region. I'm going to go from a to a. All right, so it's the net area of a stick. There's no thickness to it, so it's going to give you 0. All right, then this is the net area of, I'm going to write it as if m was positive. You could do m negative and it would work as well. So here, this is y equals m. That's a straight line, so this height is m. I'm going from a to b, and so the width is b minus a, and that's why the whole thing is b minus a times m. All right, so this is a helpful picture. If you're integrating m, you're really calculating the area of a rectangle. We did an example like that, right? Do you remember? Let's go see. Hope it isn't too far. I think it's just before this. Yeah, we did an example like that of integrating 5 from 0 to 2. We have this rectangle with width 2 and height 5, and we got 5 times 2, which is 10. Same idea with arbitrary a, b, and arbitrary m. All right, and the final one, the one I find the more interesting, I'm going to draw a picture as if b is in the middle, but really it would work in every single case. Let me put y equals f of x positive. This is part of the reason this is not a proof. I'm not going to handle every single case. I'm not going to handle f being negative. I'm not going to handle b being less than a in all of this, but I just want to give you an idea of why this is true. All right, so if we take the integral from a to c, I'm going to get the net area of all of this. But I can compute this in 2 steps. I could divide the same region and split it up at B, right? So I would get blue, all right? So blue is from A to B, so this would be the integral from A to B. And then this pink part, well, that's still, I mean, the top is still y equals f of x, but I'm going from B to C, so it's going to go, the bounds are going to be different, but the function will be the same. All right, so that means that this is equal to this plus this, the 2 different parts of the area. So that's all. All right, let's try an example. Oops. Let's try an example. I have example 4.2.1 here. I'm going to give you the value of some integrals. The integral from 1 to 2 of f of x is 3. Integral from 2 to 4 of f of x is 6. The integral of 1 to 4 of g of x is minus 2. All right, and I'm going to ask you to use that information. I'm not giving you f, so you can't compute anything separately, but I'm asking you to compute to use this information to compute some of the integrals. So integral from 1 to 1, that will be 0 because my 2 bounds are the same. So that's property 1, this one right here. Now the integral from 2 to 1, I don't have. I have 1 to 2, so I'm going to need to switch the 2 bounds. So I'm going to put 1 under and f on top. And from property 2, I know that when I switch the bounds, I need an extra minus. So this is the one I'm going to use, and all it's going to cost me is an extra minus in front. Now this I have to be equal to 3, and so I'm going to get minus 3. All right, so if I want the integral from 1 to 4, I don't have that here, but I do have 1 to 2 and 2 to 4, so I'm going to place them together. Notice that this one is a different function, so I can't use it here. I need to use these two. And so I could either do it algebraically, say I'm going from 1 to 2, and then from 2 to 4, or you could draw the picture even. All right, so as long as that middle bound is the same, so let me highlight all of this. All right, so I need to start at A. Then whatever pit stop I'm making needs to be the same, and I need to finish at C. A will always be a plus right here. You might need to change the bounds afterwards, but when you rate it as a pit stop, it is a plus in between. All right, so here I do have the same end, the same start, and the same pit stop. All right, so I'm told that 1 to 2 is 3. I'm told that 2 to 4 is 6. So in total, I get 9. Let me give you the geometric approach. So I could draw a picture from 1 to 4, put 2 right here. I have my function, whatever that function is. And so I'm given that this area here from 1 to 2 is 3. I'm sorry for not writing x, I really didn't have the room. And from 2 to 4, f of x dx, we're told that that's 6. And so the total, well, the total area is 3 plus 6, which is 9. All right, and the only property I used here was property 6. Let me just check that it's 6. Yep, right here, property 6. All right, let's try this last one. I have the integral from 1 to 4 of 3f of x plus 4g of x minus 5. I'm going to start by splitting this. So I'm going to get the integral from 1 to 4 of 3f of x dx plus the integral from 1 to 4 of 4g of x dx plus the integral from 1 to 4 of minus 5 dx. You could put the minus outside, either way is fine. So that was property 4. And then I'm going to pull the constants out. So I get 3 times the integral from 1 to 4. I get 4 times the integral from 1 to 4. Oh, x disappeared. And here, I have just a constant. So I'm going to use the mb minus a formula. So this one is property 5, the one that tells you how to find the area of a rectangle. And then here I have by property the constant that was, oh, sorry, that was 5. Sorry, wrong constant here. This one is 3. All right, so the rectangle is 3. The constant coming out is 5. All right, now I can compute every piece. The integral from 1 to 4 we just found in C. That was equal to 9. The integral from 1 to 4 of G I was given minus 2. And then I get 5 times 3. So I get 27 minus 8 minus 15. And that's 4. All right, good. We'll do a few more examples in the next video.